Today we're going to take a look at the last piece of the puzzle. If you look at, for example, what we covered so far, let's go back to our analysis flowchart. You will find that from this structure, I showed you this flowchart many times already, right? We use that to find out which test is appropriate for what data. We covered the majority of tests listed on these 4 different decision trees. Okay, the only thing remaining is what do we do when we cannot use the notion of the mean? And that's where the non-parametrics come in. Okay, so today we're going to start discussing non-parametric tests. All right, so I don't know if you realized or not, but the majority of things that we discussed in this class were revolving around 2 data types. We actually discussed 3 data types, right? We talked about numerical data, also called continuous or interval. We talked about nominal data and ordinal. We did a lot of tests with continuous numerical data. And most of these tests, well, not most, all of them actually, implied that somehow your distribution is normal, right? We first tested one population sample, and we required that sample is normally distributed. And we said, well, let's take a look at 2 populations, matched pairs or independent samples. And we said, well, in this case, either your sample, individual, each one of them has to be normal, or differences between matching observations have to be normal. And then we said, well, how about more than 2 populations? And then you have ANOVA, or one-way ANOVA or 2-way ANOVA with blocks, and even then we required each sample to be normally distributed. So each time when we discussed not normal distribution, but interval data, continuous data, normality was a requirement, and we checked that, right? We looked at the normal quantile plot, and then we fit the normal distribution and ran Shapiro-Wilks test. But everything checked out so far. Well, that basically brings the natural question, well, what if you check normality for any one of those tests and it's not there? So it's violated. Either differences are not normal or samples are not normal, so something doesn't look normal. In fact, I believe that in the majority of the practical situations that you can encounter in the real life, that's what you will see. Normality is actually a tall order, oftentimes. So a lot of data sets out there that you collect, they do not satisfy normality requirements. Then what do we do? So we need to discuss that. Also, when we talked about nominal data, it was in the context of proportions, right? We tested single population proportion, like what percentage of people get gift cards on Christmas, right? So some of the respondents, they said, I don't get gift cards. Some said, I do. And we looked at proportions. So percentage of people voting for Republican versus Democrat. Then we compared 2 populations proportions, right? So what happens if we redesign our product? Will we grab higher market share? Will percentage of our sales get higher as a result of the product redesign? So we looked at nominal data, and in nominal data, we discussed primarily percentages or proportions, right? So that brings up another interesting question. How about ordinal data? What if your data are ordinal? Then what do we do? We should have some sort of tests in this case, right? But we never touched ordinal data so far in this class. So therefore, methods that we're going to discuss, they apply. They're called non-parametric statistics, and they apply to these 2 cases. When your data are continuous, interval, and the normality is not the case, so something is not normally distributed, or if your data are ordinal. Okay? The reason why these methods are called non-parametric is, well, it's basically, it is what you hear. Non-parametric means that there are no parameters involved. So therefore, when we're going to discuss these tests in non-parametric chapter, we will not use anything like what we did before. There will be no percentages or proportions. There will be no means or standard deviations. So none of these things that we used to look at when everything looked normal, when your samples were normally distributed or differences were normally distributed. Okay? So therefore, we're not going to use the idea of the mean or median. Well, actually, these tests, an argument can be made that non-parametric tests are not about the mean, but they are rather about the median. But we're not going to use the mean anymore. Okay? So in all these tests that we will discuss, there is no such thing as a mean. Well, then the question is, if we don't use the mean or parameter, what do we use? So the mean is replaced with the general idea of population location. Okay, so let's discuss what is that, a population location. Population location is a very weird and vague idea. I have to be honest with you, okay? It characterizes in general where the population is positioned on the horizontal axis, okay? What is the location or positioning of the population? And also it considers what's the shape of the distribution in general, right? So, for example, let's take a look at these two distributions. They're kind of good candidates for non-parametric techniques, right? If, for example, I take a sample, and construct a histogram, and then after that on the top of the histogram, I draw a smooth line that pretty much follows my peaks and valleys, follows the bars, right? And bars, and the smooth line, it looks like that. Well, when I plot the histogram, obviously that is not going to pass the test, right, for normality. This is a bimodal distribution, probably slightly skewed in the right direction, in the positive direction. So it is not normal. Okay, so I have two populations, two samples, right? Red one and blue one. Now, both of these populations not normally distributed. So now we discussed that, right? Before. Let me kind of remind you. Why do we not use? Why can't we use mean in this case? Well, the idea is, let's say that this is your distribution, just like what I had before, on the picture, right? Looks like that. What's wrong with the mean? Well, if I compute the mean, probably mean is going to end up somewhere over here, right? In the area where I do not have a lot of data because I have a valley, right? Lacking of data. If anything, this is a bad representation. Remember, at the beginning of this semester we said that the idea behind the mean, median, and mode, they're supposed to describe data set center. So that technically, mathematically is the center of my distribution, but if anything, I have less numbers like that around the mean, right? So it's not a good representation of the center, right? I have a lot of data in the right portion of in the left portion of the distribution. So this is a good candidate for the mean because I have a peak right over there. Well, that mean ignores completely the right portion, which is also substantial, right? Then a similar argument can be made. What if I go ahead and set my center of the distribution right here, which is also a bad choice by exactly the same argument in this case, because in this case I'm ignoring the left part of my distribution. So no matter where I try to find the center of my distribution, I have every single choice has its own deficiency, right? So there is never a perfect number that basically tells me, yep, that's a good representation of my distribution. So therefore, we're not going to use mean at all. That's the idea behind non-parametric statistics, okay? Instead of that, we're going to use the idea of location. So location is, well, let's say here. Distribution is ranged from A to B, and it's bimodal, right? So this is pretty much how you describe that specific population. Very vague and non-specific, right? Well, as vague as it may be, what I can say from this picture, from what I can see, right, visually, these two populations, they are very similar to each other, right? They're located in approximately the same place on the horizontal axis. They have about the same shape. And if I impose them, like one lay over on the top of another, right, they will follow fairly closely the same pattern. So therefore, instead of saying mean 1 equals to mean 2, now I'm going to say population 1 location is the same as the population 2 location, right? So alternatively, here's what I can have. I can have two different pictures. If my population shapes are the same, let's say shapes are the same, okay? But one is shifted with respect to another to the right or to the left. Then I'm still going to say that locations are different. Even though the size and the shape of the distribution looks about the same, but they are not in the same place, right? They don't occupy same space, so to speak, horizontally, right, on the horizontal axis. So if I have this picture, my population 1 is shifted to the left compared to the population number 2, then I'm going to say instead of mu1 is greater than mu2, I'm going to say that location of population 1 is to the left. Well, actually, mu1 is smaller in this case, right? Mu1 is less than mu2. Population 1 is located to the left from the location of the population number 2. If I have the reverse picture, 1 is shifted to the right, and I'm going to say that population 1 is to the right, or greater than population number 2, right? So what used to be, remember when we compared two populations, we discussed that everything is about mu1 minus mu2. And our three forms of hypothesis are going to be mu1 minus mu2 equal to 0 versus not equal to 0, right? Mu1 minus mu2 is greater than or equal to 0 versus less than, and also less than or equal to 0 versus greater than, right? These are three forms of hypothesis that we decided to test when we're talking about two populations. Well, since there is no mu anymore, we have to use the idea of location. So what used to be mu1 minus mu2 equals to 0 versus not equal, we're going to say that the locations are the same, or no, they are not the same, they're different. One is on the right from another. Which one, we don't really care, they're not the same, okay? What used to be mu1 minus mu2 greater than 0, now we're going to say that location of 1 is to the right from the location of 2. And what used to be mu1 minus mu2 less than 0, we're going to say location of the population number 1 is to the left, or smaller than the location of the population number 2. So, very similar to what we had before, we just replace difference of mu's with the idea of location. And we say where it is. Is it different? Is it to the right? Is it to the left? That's how our alternative hypotheses are going to look like. Okay, so let me skip these couple of slides because we pretty much discussed them. Now, before getting into the specific problems, let me tell you how the tests are being performed. Okay, the tests are performed in a very weird and unique way. So we're not going to do that manually. I'm not going to ask you to do anything, any kind of computations on the homework or on the exam. But let me show you, kind of give you an idea of how the tests are actually being conducted. Let's say I have two samples with only 3 numbers in each of the sample, okay? So here's my sample number 1, S1, and here's my sample number 2. Now let's say in the sample number 1 I have these numbers. I have number 10, 15, and let's say 17, okay? And let me actually draw them closer together. Sample number 2. And sample number 2 has numbers 20, 25, and 27. Something like that. Okay? So if and again, let's say I'm testing hypothesis. Locations are the same versus locations are not the same. Okay? So how about this? I'm going to draw a histogram or a distribution, okay, of these two things. So here's how my histogram is going to look like. First of all, my sample size is very small, right? That kind of sucks. Every time, by the way, when you have small data sample, that brings an interesting question. How do we test for normality, right? How do you test, like this sample, number 1, does it come from normal distribution or does it come from non-normal distribution? Oh God, three observations, right? When do we, when we have a sample, if we have a sample with a decent size, then we can talk about distribution and statistics and all these things, right? What do you do with 3 data points? Nothing really. You can't do much about that, right? They may or may not come from normal distribution. We wouldn't know, we wouldn't be able to even find out from just 3 numbers, right? It's just not possible. So therefore, a good rule of thumb is when your sample size is really small, okay, like this one, may be normal, maybe not normal, we don't know, and we're not going to make any assumptions, right? So therefore, pretty much every time when you have small sample size, you have to use non-parametric techniques, because there is no way to test for normality. You can't reliably test for normality 3 data points. It's just crazy, okay? So every time when you have small sample, something like 3, 5, 10, even 20 observations probably is not enough, okay? If you have 30, sample of 30, then probably now you have a case. Now you can test for normality and say, oh yeah, look, it's normal, or is it skewed, or is it bimodal, not normal, something, okay? But 3 items, no way, all right? So I'm going to draw a schematic representation of each one of them, all right? So here is my, for example, sample 1, I'm going to use cross to denote the numbers, and sample 2, I'm going to use the circle, okay? So sample 1 starts with 10, the next is 15, somewhere here, and the next is 17, somewhere here. Here's my sample 1, right? And sample 2 starts at 20, which is somewhere over here, and then it goes to 25 right here, and it goes to 27 right here. So by looking at these distributions, first of all, spread is the same, right? The range. 17 minus 10, that's 7, and the same for sample 2. So here's my sample 1, and here is my sample 2. So shape, I'd say, is about the same, but what about the position, horizontal position? What do you think? Is it the same or is it different? Different, right? From these numbers I can tell that, hey, my my population number 1 is probably to the left from the population number 2. Agree? Because entire distribution is shifted to the left. Okay, so here is the idea behind the test. All the tests pretty much that we're going to conduct. Tests are not performed based on these numbers, 10, 15, 17, 20, etc., but based on ranks. Okay? What do I mean? If I put together both samples and align them from lowest to highest, so I get 10, next is 15, next is 17, then I have 20, 25, and 27. Okay? All right. So this is rank number 1, because it's lowest number, then it's number 2, 3, 4, 5, and 6, right? So my sample number 1 contains numbers ranked as 1, 2, and 3. So these are ranks, right? Oops. Ranks. And here I'm going to have ranks as well. And sample number 2 has 4, 5, and 6. Okay, cool. Now I'm going to have to add the ranks together. Okay, so therefore I'm going to compute rank sum. So here the sum is going to be 6 for the sample number 1, and here the sum is going to be 15 for the sample number 2, right? So that basically tells me that sample number 2 contains higher ranked numbers. Therefore, the rank sum is higher. Therefore, I kind of have an indication that maybe, because sample 2 altogether ranks higher, maybe sample number 2 is to the right from sample number 1. Okay? And that points me towards my alternative hypothesis, that sample 2 is to the right from the sample number 1. Right? So the higher the difference between these ranks, sums, not ranks themselves, but the sums, okay? 6 and 15. The higher the difference between these two numbers, the more I have the confirmation that populations are differently distributed. Their locations is different, okay? One is either higher than another or lower than another. Only if the rank sums would be similar or closer together, then I would say, yep, locations are not that different because ranks are very similar. In fact, here's what I'm going to do, okay? I'm going to scramble these two samples. I'm going to use the same set of numbers, okay? But I'm going to kind of mix and match them, right? So therefore, here goes. Here's my sample, new sample number 1 and new sample number 2, okay? So in sample number 1, I'm going to have, let's say, 10. And here I'm going to have, let's see, 15. All right. And then I'm going to have 17 over here. And then 25. And then 20 and 27. Something like that, okay? So I mixed them, right? Same numbers, but now they're all mixed together. Okay? So obviously, I'm going to have the same ranks, right? But positioned differently. Now, in my sample number 1, the ranks are, this is number 1, 17 is number 3, and 25 is number 5. So my sum of ranks is going to be what? 1 plus 3 plus 5 gives me a 9, right? And in the sample number 2, I have rank number 2, 4, and 6, so that the sum of the ranks is going to be 12. Do you see how they got closer, the sums of ranks? So therefore, now samples are getting brought closer together. And if I look on the picture, actually, here's how it's going to look like. My sample number 1 has a 10, then it has a 17 right here, and it has a 25 right here, okay? And my sample number 2 has a 15, which is right here. Then it has a 20, which is right here, and it has a 27, which is right here, right? So here is my sample number 1, and here's my sample number 2. Do you see that they overlap now compared to the previous case? Same numbers, but now my samples are kind of mixed together, right? So therefore, the difference between the sums of ranks is not quite that large anymore, right? It used to be fairly large. It used to be 9, right? Between 15 and 6. Now it's only 3 between 9 and 12, right? And the samples, you can see visual, are being brought closer together, right? So therefore, all the tests that we're going to take a look at in non-parametrics, that's the technique that they employ, all right? They're not comparing the numbers, but rather they're comparing ranks, okay, of these numbers. Make sense? So I'm not going to go into the details because they're fairly nasty, the details. If you go to nitty-gritty of these tests, it's just getting crazy. All right? So we're going to just familiarize ourselves with how the tests are performed and what exactly are we testing. Okay, so the first thing that we're going to look at is something that's called Wilcoxon rank sum test. And we know where the rank sum is coming from, right? We compute the ranks for each number inside a sample, and then we add the ranks together. So therefore, Wilcoxon test essentially is testing sums of ranks. In JUMP, it's actually called just simply Wilcoxon test. So they skip the part sum, rank sum, right? So they call it Wilcoxon test. End of story. Now, Wilcoxon rank sum test, actually, here's the important piece, okay? It is used when your samples are independently collected. And your data can be either ordinal, or it can be non-normal interval data, okay? And because samples are independent, we have to check each sample for normality. Remember, that's what we did when we used the t-test, right? We said, every time when you use the t-test for independent samples, you test sample 1 for normality and you test sample 2 for normality. That's precisely what we're going to do here. If our samples, one of them at least, does not pass the normality test, that's it. We can't use t-test, and therefore we have to use Wilcoxon rank sum test. Okay? But this test is pretty universal, pretty cool. It tests two things: ordinal data and interval data if distribution if at least one distribution does not look normal. Okay? Applies to both data types. And again, very important point is that samples have to be independently collected. Okay? All right, so without further ado, let's take a look at this problem. Painkiller. I told you before that pharmaceutical companies, pharmaceutical industry is one of the biggest users of statistics. right? Because how do you know, for example, that let's say that there is a company that came up with the chemical formula, and they claim that this is a new painkiller, which is better than established painkiller in the market. Established painkillers in the market are aspirin, Advil, Tylenol probably, right? A couple of others, probably ibuprofen, right? So these are names that everybody knows. And let's say that a certain pharmaceutical company comes up with a new drug and says, well, that seems to be better than aspirin, okay? Now, of course, you can't make these claims without statistical confirmation. So here is how they can do it, okay? Well, first of all, you can't measure pain, right? You can't hook up a person to a painometer and measure the pain on a numerical scale. So therefore, we have to rely on people's subjective feeling, right? How do they feel? So here is the idea how the trial can be performed. We can take a bunch of people who are in pain and split them roughly half and half, right? So 2 groups. And group number 1 will get aspirin, traditional drug, but we're not going to tell them that this is aspirin. We're going to tell them, hey, here is the painkiller, right? Whatever it is, painkiller. But we know, of course, because we are conducting the experiment, we know that this is aspirin, right? Take this thing and, an hour later we'll ask you again, what do you feel about the pain? So, gradation from 1 to 5, right? 1 means that I don't feel any different. So pain is still here, nothing happened, this pill sucks, right? Number 2 is, yeah, I feel somewhat slightly less pain, but it's not a whole lot, so pretty bad also, right? 3 is somewhat effective, that means 50-50, and okay, right? There is some effect, but it's not huge. 4 is quite effective, that means for the most part I feel no pain, but still there is some left. And 5 means extremely effective, pain is gone, a very good drug, no side effects, no pain, right? So 1 is great, 1 is very bad drug, doesn't work really, and 5 means effective. So one group takes aspirin and we ask them, what do you feel on the scale from 1 to 5? Another group takes a new drug, experimental, but again we don't tell them that this is a new drug. We just tell them, here is a painkiller for you. In an hour we're going to ask you again, what do you feel? And you tell us, 1 through 5, right? Okay, so we collect samples and now we have to test them. And what exactly are we testing? I mean, if I come up with a new formula that says painkiller, but it's not any better than aspirin, should I put it on the market? I don't know. It's going to be hard to market, right? Because everybody knows aspirin. People take it for, I believe it's also anti-clotting agent, right? A lot of people take it, like when they have blood clots, they take aspirin because it kind of thickens your, or thinning, it's a blood thinning agent, right? It thins your blood so that you don't have clots. Aspirin is good, and this new drug, I mean, if it's not better, then why would I buy it, right? It's not tested, it's not proven by the market. No, I'm not going to do it. So the only reason probably why companies would go with a new drug on the market is a better drug, statistically better drug, right? Okay, so here is what we're going to test then. Our alternative test, remember, we start formulating hypothesis with alternative. It's easier because that hypothesis tells you what is that we're investigating. Since our belief could be that new drug is better than aspirin, that's what our alternative is going to be, right? The new drug is better. How do we express this statement in the formal statistical form? Well, here, right? If the new drug is better, then it will receive more 5s and 4s than aspirin as compared to 1s and 2s, right? So I expect in general the new drug to receive better ratings, right? So therefore, location of the new drug, because 5 is better and 1 is worse, should be shifted to the right compared to the location of the aspirin, right, population. So aspirin in general should receive lower ratings than the new drug. Then I would say, yep, it doesn't work the same on different people, but in general, overall, if I look at the distribution as a whole, the new drug actually performs better than the aspirin, okay? So therefore that becomes my alternative, that the location of new drug is to the right from the location of the good old aspirin. And my null is going to be that no, there are no different reaction of people to the new drug and to the traditional aspirin is about the same. That's what I'm going to test. Okay? All right, now let's go ahead and look at the data. Let's download, there is a data file called new drug out there on Scholar. So download that file and then open it up. Okay. So here is my file. And you can see that the data are actually ordinal, right? Do you agree that data are ordinal? They are, right? Yep, they're not numbers, they're actually categories. But you can see that I labeled them as continuous, right? So I'm going to, even though the data are ordinal, I'm going to treat them as continuous, but I will perform the right test on that. And what exact test? Let's find out. Okay, let's be formal about that. Let's go with our magical school bus. No, magical flow chart. All right, so which one do I pick? Describe a population, compare two populations, compare three or more, or is that a relationship? Under what umbrella does that fall? Compare two populations, right? I'm comparing new drug with existing, right? So I start over here, comparing two populations. Next question says data type. Well, ordinal, right? I feel better, slightly better, a lot better. That's ordinal data. Experimental design. Ever important question, right? Do we have matched pairs or do we have independently collected samples? What do you think? Let's go back to the description. So, independent, right? Because they took 30 people, split them half and half, random group 1, random group 2, right? There is nothing that links people on the same line, right? If that would be the same person, that would be matched pairs. It's a reaction of the same person to different drugs, right? But can I give one person 2 pills and say they feel less pain, but here is 30% of this effect is due to drug 1 and 70% or 50-50 or whatever. I cannot, right? So it's all or nothing kind of deal. I take a person, I give them just one drug. I can't split it between new and aspirin, right? So it got to be independent samples. I cannot make them matched. You cannot replicate same person, the same level of pain and same reaction to the drug, right? That's just not biologically possible. So therefore samples have to be independently collected, okay? All right, so independent samples, and right there is the answer for me, okay? It's Wilcoxon Ranksum test, or it's called in JUMP simply Wilcoxon test, or Mann-Whitney. I believe Mann-Whitney actually, JUMP doesn't do Mann-Whitney test, okay? But Mann-Whitney in general is it's analog of Wilcoxon test, okay? The reason why I have it here is this is my old flow chart from a year ago when I used SPSS. And SPSS uses Mann-Whitney test. Okay, so we're going to use Wilcoxon test on that one. All right, so let's go back to our data. And remember, what do we do when samples are independent? We have to stack them, right? Because that's what JUMP requires. If samples are independent, they have to be stacked. All right, let's stack them. So I go to the tables, stack, and I stack new and aspirin together, just like that. And my data, I'm going to call, what do I call it? Reaction, right? Reaction to drug. How do I feel after I take anti-pain medicine? And the label that would be drug, right? I have 2 levels, right, of this factor. I have new drug and I have experimental and aspirin, right, traditional. Okay. So here is my stack data, okay, 30 people, 15 took new and 15 took aspirin. All right, and first of all, actually, even before we do that, let me go back. Remember, in the previous lecture, we discussed that before you start jumping and testing hypotheses and throwing numbers around yourself, it's a good idea to look at the picture, right? So let's look at the distribution, right? So new and aspirin, let's look at the distribution. and I'm going to stack the distributions so that they look horizontal as opposed to vertical. All right, so here is my distribution for the new drug, and here is my distribution for the aspirin. By just looking at these two shapes, is that a fair statement that my new drug received more high ratings and less low ratings compared to the aspirin? Or is it not a fair statement? What do you think? So here's my new drug, right? It has a high bar on the highly effective side, right? It received a lot of 5s, right? And it received some 4s, right? And then some 3s. But and then a little bit on the low side. Christian?
Question. I stacked the new and aspirin.
Uh-huh.
And I put them both in the stacked columns and just trying to redo it. And it has one of them is uniform, like distribution.
Uniform? Did you plot them separately, or is it?
Okay, so I'm labeling it by. I put both as continuous.
Yeah.
Okay.
Yeah. So I went to my old, initial original data set, and I just plot the distribution of one and another, and that's what comes out, right? And if I look at the aspirin, it does not receive a lot of 5s, right? It does actually receive a lot of 4s, but it's also high on the low end of the spectrum, right? Quite a number of people said it's not effective at all, or it's just a little effective, not huge. So it may be an indication that, in fact, the shapes of these two different distributions are fairly different, right? And my new drug received more high ratings compared to the aspirin, right? So that's what I'm seeing visually. It's not rigorous, of course, right? So now I have to go back and test the hypothesis. All right, so here's my stack data, and here's what I do, right? I go to fit y by x, okay? And I'm measuring the response, which is a reaction, right? My numerical column. Reaction, and the factor is drug. Is the reaction to different drugs different? That's what really I'm studying, fit y by x. And when I hit OK, first of all, it gives me just a basic plot, right? From this, I can't really tell because, probably a lot of points are stacked over here, right? It gives you 5 different levels, right? But I know that every level has multiple different points, right? So therefore, I can't really tell anything. I mean, these two look identical, so that doesn't bring me any information at all. So now let's go ahead and do the analysis, right? We decided that's going to be Wilcoxon test. Agree? All right, so I'm going to go to the red triangle, of course. And there is a option right there that says non-parametric. Okay? Now, there is a non-parametric test, Wilcoxon test, right there. Okay, and we can use that. But, well, let's actually try. Let's go ahead and click on the Wilcoxon test, and it will give you the output. Okay? But, as you can see, well, and let's actually take a look. Remember I told you that the way how test is conducted is we rank numbers, and we add the ranks, right? So here's, well, jump calls them not ranks but scores, and here is the score sum, okay? So aspirin, total sum of ranks, in the aspirin column was 185.5, and in my new drug column was 276.5. So, in other words, observations in my new drug column, they scored higher, right, in general, which is good, which actually points towards my alternative, right? They have higher scores, so therefore distribution is probably more on the right from the aspirin, okay? But you can see that the way how test is performed is actually it's using normal approximation for the test, or Z or chi-square approximation, right? There is another option. If you go to the red triangle menu and go to the non-parametrics, this is the one that we picked, Wilcoxon test, right? You see, second from the bottom says exact test. The test that was performed right now is an approximation, normal or chi-squared approximation, right? So now we're going to use the exact test. So Wilcoxon exact test. That's the option that I'm going to use. Click, and it gives me the output. All right, right there. Now I consulted with JUMP representatives, and what I was told is You can see it right here, actually. Okay. Remember when we tested the hypothesis about two populations or one population using the t distribution? We had three options, right? Probability greater than t for the right tail, probability less than t for the left tail, and probability greater than absolute value of t for two-tail test, right? So let's take a look at this output. Probability greater than absolute value. That is a two-tail test, right, by analogy. So by default, it does for you two-tail test. But here is the probability greater than s, and that is the right tail test. And you can see that because if you use the two-tail test, it's going to be symmetric, right? So therefore, the p-value is going to be twice than the p-value for the one-tail test, okay? And you can see that 0.0336 multiplied by 2, you get that number, 0.0673, right? So half of this p-value is that number, which is the what we're looking for. That's our p-value, right, that we need really, because our hypothesis, remember, it's not just that drugs are different. More specifically, we're looking to see if the new drug is better, right? So we're looking in the right tail of the distribution. So it's a one-tail test, actually, not a two-tail test, okay? All right, so now that I have a p-value, what do I do with it? Well, I have to say that the p-value, and that's a one-tail test p-value, 0.0336 is less than 5%, right? If it's less than 5%, what do? Keep the null or reject the null? Yep, I reject the null, right? If I reject the null in favor of alternative, let's see what that means. Let's go back to our hypothesis. Reject the null that the populations are the same in favor of alternative, and alternative says that my new drug distribution is to the right from the aspirin drug distribution. So do I have a confirmation that statistically people react better to the new drug than to the aspirin? Yes, I do, right? So my alternative I found in favor of alternative, which means that in these clinical trials, new drug performed better than the aspirin. That's what kind of stuff companies would submit to FDA for approval, right? Because FDA will not take just, hey, we think this is a better drug. What do you mean you think? You need to conduct clinical trials, and that's what it is. Christian?
So, what's the difference between, let's say I took aspirin and you took the new drug? How do you quantify the level? What's the difference between a 4 and a 3? Let's say everybody picked a 4, when it should be a 3, but it's not as effective. Like you have a type 1 error.
Oh, yeah. It's a subjective test, if that's what you mean, right?
Yeah.
So they asked me how do I feel. Let's say we were in the same level of pain, and then we got the same reduction of the pain, but you say it's 3, and I say it's a 2 reduction, right? Yeah. There is always that subjectivity.
Would that come with a margin of error? When that comes into consideration?
Margin of error? Well, here, margin of error, you can apply margin of error to things that you can measure, right? Yeah. Here, you can't really say, even me, right? Today, for example, I'm in pain. I take a pill. I got, some reaction to the pill. I'd say I improved quite a bit. Tomorrow, I'm in the same level of pain. I take the same pill, and I say, well, I don't think it's the same. So even me, on different occasions, I can evaluate things differently, right? Yeah. So there is always subjectivity inherent to this test. Yeah. So the results should be taken with a grain of salt, essentially, right? But that's the best we can do, right? If we could measure the pain, that would be ideal. Hook up a person, to the painometer, measure the intensity of electrical signals propagating through the nerves or something. I don't know, right? Measure the dilation of pupils, the pulse rate, the perspiration, or something, right? And then decide based on that. But we're not quite there yet, okay? We suck when it comes to medicine, right? We think that we're smart, but we're not. We don't really know how the body works. Can't measure a lot of things. We're like monkeys, really, right? Okay, so, make sense? All right, good. Now, let's take a look at what happens if you don't have independent samples, right? Remember, the Wilcoxon test is applicable to both, thank God, to both ordinal data and non-normal numerical data when the samples are independent. So this is a universal test. Okay. In fact, on the one of the problems on the homework, I give you a hint probably, right? You will find that this is a Wilcoxon test, but the data are not ordinal. So here in class we used ordinal example. On the homework I give you a numerical example with the Wilcoxon test. Okay. If samples are not independent, they are matched pairs, then unfortunately we have to use two different tests. Okay. When data are interval, it's test number one. When data are ordinal, it's a completely different test. So let's talk about what happens when the data are, where is that? Yeah, right there. When the data are matched pairs and they're numerical, but the normality is violated. Okay? Then we're using something that's called, well, there are two tests we're going to study. So today we're going to study Wilcoxon signed rank sum test. So there is a signed version, okay, of the Wilcoxon test. And that applies only to the numerical data. Matched pairs, numerical, matched pairs, numerical data. Okay? When the assumption of normality is violated. That's when we use Wilcoxon rank sum test. When we have matched pairs ordinal data, then we're using signed test. Okay? So today we're going to look at Wilcoxon signed rank sum test. Okay? And the next slide actually tells you the story, right? Pretty much. Signed test, oh sorry, that's not the right one. This one. Wilcoxon signed rank sum test is used when you have matched pairs, samples are not independent, and also two populations are not normally, the differences between the matching observations are not normally distributed. So I should correct it here, okay? That's not an exact statement. It says two populations of interval data, but not normally. What's not normally distributed? The differences. Remember when we used the matched pairs t-test, we said, doesn't matter what sample 1 looks like, doesn't matter what sample 2 looks like, as long as differences are normal, we can use t-test. That was the rule, right? We computed the population, the differences between matched observations. Okay? So, same here. If your sample 1 is normal or not, I don't know, I don't care. Well, I may check it, but that's not the point really, that's not important. If the differences are not normally distributed, then this is the test I'm going to use. Wilcoxon signed rank sum test. Individual samples can be normal, that's fine. But if differences are not normal, that breaks the deal. Okay? Can't use t-test, I have to use Wilcoxon signed rank sum test. Okay? So, again, to give it a practical spin, let's take a look at this problem. It's actually a very old problem. We don't see these things anymore, right? The blockbusters. When you rent the movie on the tape, VHS tape, or on the DVD, right?
There's only 12 of them left, and they're all in Alaska.
Really?
Fun fact.
Only 12 blockbusters left? What happened to them? I mean, at one point, I believe there were like boxes outside of stores, right? Where you could.
The red box.
Yeah, red box, DVD.
I think it's still.
They kind of disappeared. So Blockbuster, is it still alive or did they go underground?
It's just in Alaska.
Just in Alaska? So they.
Because the internet's so expensive.
Oh yeah. Oh, in Alaska, right?
Yeah.
Oh, okay. I didn't realize that. So in Hawaii, probably the same thing, right? No?
It's concentration.
Ah.
Yeah.
Alaska is half the size of Fairfax County
Uh-huh.
and 1/5 of the United States total land mass. There's about 750,000 people in Alaska.
Oh, so the population density is very low, right?
Yeah.
Extremely low. And
Yeah.
half of that population is Anchorage.
Anchorage, right?
And Juneau.
Yep.
Juneau.
Oh, that's interesting. And in Hawaii, because it's all on a couple of islands, right? The population density is high, so therefore it makes sense, yeah, economically. Okay, that's interesting. So let's go back to the times when this was an option to go to the store and rent a movie, right? Well, you can still do it online, right? So mechanically it's different, but principle is the same. So movie studios believe that adding sexually explicit scenes to the home version of the movie will increase the appeal and profitability because people will rent it more frequently, right? So here is what the executive decided to do. They took 40 movies that were rated PG-13, parental guidance under 13 years, right? And added some explicit scenes, extended version, right, of the movie. And after that, the rating was changed to R, right? And they made these movies available. So this is a family version, sort of, right? And this is an R version of the same movie. So people have an option which one to rent, online or offline or whatever, right? And they placed them out there for rent. Okay, all these things, all these movies. And they recorded basically how many times each movie was rented over the 1 week period, right? So here is the all-important question at the end. Using 5% significance level, can we conclude that adding explicit scenes increases the movie popularity? And what do we mean by movie popularity? That means that it's being rented more frequently, right? People vote with their wallets, right? Okay, so let's go ahead and close all the stuff that we don't need. That's what I'm going to do. All right, a couple of more. All right, and let's take a look at the file, PG-13 versus R. Here is the file. Let's download and open it up. Okay. All right, where is that? It's right here. Okay, so first of all, let's be formal, right, about this. Let's see which hypothesis do we need to test. And I have to go to my magical flowchart, right? It's fairly obvious that I'm comparing two populations, correct? Comparing R versions of the movie and PG-13 versions of the movie, okay? Data type. Which way do I go? Interval, nominal, or ordinal? What do you think? Are these measures or are these just random labels? What I have in the file. That's how many times the movie was rented, correct? So therefore they're really numbers. They're not labels, they're not categories, right? So therefore I'm dealing with interval data, right? Okay, well, we discussed it. Variability, we're not dealing with this. So central location. Experimental design, people, what do you think? I have two options, right? Samples are independently collected or are they matched by some criterion? What do you think? Here's how the data was collected, right? They take 40 movies and each one has two versions, right? PG-13, the basic, and then they extend the movie by adding a couple of scenes and that becomes an R-rated. So, therefore, when I'm looking at my data file, is there anything that links these observations on the same line? Number one, 772 and 815. What links them? It's the same movie. Different versions, but pretty much it's the same thing, right? So therefore, I have matched pairs, right? These are the same movies on both columns. All right. I have to go back to my flowchart, right? So experimental design is matched pairs. And next question is how the differences are being distributed. If they're normal, then we're back to our good old friend t-test, right? But if they're non-normal, then I have to deal with Wilcoxon signed Ranksum test. So therefore here is the point where I have to test differences for normality, right? Let's go back to the file. Remember how we did that? I create a new column, right? So column number 3, I'm going to call differences. By the way, when I taught this course using SPSS, it's the same thing really. So SPSS does not compute differences between two columns. You have to do it just like that. You have to go to the menu, say formula, which we, by the way, didn't do, right? And in the formula you have to, so they follow pretty much very similar pattern of analysis. All right, so column properties, I have to go to the formula and edit formula, and the formula is simply what? PG-13, so I'm gonna have to click PG-13 minus R, okay? Just like that. Difference between the two columns that I have. And then I click OK. And then I click OK. And here are the differences. So now I have to investigate if they're normal or not. Well, let's do that. distribution, right, of differences. That's what I have to look at. Okay? So here is the distribution, and let me stack it. What do you think? Without even using any tests, like Shapiro-Wilks test, what do you think? Will it pass the normality test? No, no way, right? So if I look at the normal quantile plot, oh god, as bad as it gets, pretty much, right? All kinds of non-normal. So let's just be formal about that. Let's run the Shapiro-Wilks, right? So I have to go to continuous fit normal, and in the fitted normal I have to ask for goodness of fit. My p-value is very small, therefore I reject the null that data are normally distributed if I want to be really and truly formal about that, right? So these samples are not normally, these differences are not normally distributed. This is what I'm testing. I'm testing differences, right? Between sample 1 and sample 2. Not normally distributed. Right? It says node. Null is data is from the normal distribution. Small p-values rejects the null, right? And we do have small p-values, so we reject the null. All right. Okay, so now let's go back to my flow chart. Distribution of difference is non-normal, and I have to use Wilcoxon signed Ranksum test. But before we do that, so we have really a couple of steps missing, right? So we have to do the test. Before we do that, let's actually formulate what is that exactly we were testing, right? We're saying that R-rated movies are more popular than PG-13. That's the belief that we're testing, right? That's my original statement when I just read the problem. Some executives believe that PG-13 movies can be made more popular if you extend them and make them R-rated, right? So therefore, the distribution R should be where? Higher or lower than distribution PG-13? To the right. Higher, right? Should contain higher numbers in general. And that's precisely what I'm testing. Now, we'll say locations are the same, there is no difference. PG-13 and R, same distribution, same location, so therefore has no effect. Okay? But my alternative will say that location of PG-13 is to the left from the location of R, or which is the same, R is to the right from PG-13, right? It has in general higher numbers. Okay? It's heavier towards higher numbers. Okay. Well, without further ado, let's go ahead and do the test. So, and I do the test actually in pretty much the same way as I did the test for matched pairs when distribution of differences was normal, okay, using the same exact menu, right? So I go to Analyze, I go to Specialized Modeling, and at the bottom of this menu I have paired, matched pairs right there, okay? So matched pairs, now I have to bring them into the Y, right? Because you can see that I need to have two things, right, in the Y responses. So my column number 1, PG-13, and my column number 2, R. I believe what happened in the past when we tested this hypothesis, JUMP kind of reverses that, right? So if I'm bringing PG-13 number 1 and R number 2, it will test actually the difference of 2 minus 1. In other words, R minus PG-13. We'll see actually. So this is what I did, right? I put PG-13 first and R second, and when I click OK, look at that. It says it testing the difference between R minus PG-13. So what I was saying, right? What you put first becomes second, and when you put second becomes first. So it tests essentially mu2 minus mu1. So you have to be kind of mindful of the order how you put it in, right? So if I'm believing that R is more frequently rented than PG-13, then difference between R and PG-13 should be positive, right? If that difference would be reversed, PG-13 minus R, then I would be testing for the negative, right? Because PG-13 is less, R is more, so difference is negative, right? Less than 0. But now R minus PG-13, that has to be a positive difference. And this, by the way, by default, it tells me what? It gives me the t-test, right? This output basically tells me that if you're using a t-test, then there it is. It's in front of you, okay? But I'm not using t-test, right? We just discovered that differences are not normal, so therefore t-test is a no-go. Instead of that, we have to use Wilcoxon signed Ranksum test. Where is that? Well, here I go to the matched pairs, red triangle. Do you see that? Option, Wilcoxon signed rank test. That's the one. Okay, so when I hit OK, I'm testing which tail of the distribution? I'm testing that R minus PG13 is greater than 0, right? R is more, PG13 is less, so therefore difference between R and PG13 is positive, right? So therefore I'm testing the right tail of the distribution, correct? So that means that I'm looking at probability greater than S, where S is whatever it is they're computing, right? Some statistic about these two samples, all right? So since I'm using probability in the right tail, I have to use greater than S. What does it tell me? Very small, right? Less than 1%. So therefore, coming back to my original hypothesis, there it is, right? Small p-value, I reject the null in favor of alternative. So what do I say? Is that belief statistically confirmed that if you spice up the movie content, it's gaining popularity? Looks that way, right? Things are not normal, so we use nonparametric test, and nonparametric test tells you that, yep, statistically, the R-rated movies are being rented more frequently than their PG-13 versions, right? So therefore, when executives believe that, if you spice things up, they'll sell better, that is true. Statistically, it's true. Make sense? Christian?
Question for column 3, the formula you put in is PG13 minus R, and it gave you the negative values. I thought R versus PG13, R minus PG13.
And that gave you positive values, right? Yeah, no, it doesn't matter because, exactly, it will just flip, right? But if it's non-normal shape one way, if you flip it around, it's still non-normal shape, right? So it doesn't really matter what you test, 1 minus the second or second minus the first. If it's non-normal, it will show up either way, right? So when you test the differences for normality, however you construct the differences, will not have any effect on the results of the test, okay? Any questions, concerns, complaints, sarcastic comments? And we're out of time for today, right? So I'm going to stop the recording right here, and tomorrow we'll go over the exam, which we had today. We'll go over the homework. There are 2 problems out there, okay? And then we'll finish up the non-parametrics. We have, how many more tests? We have sign test to discuss. We have Kruskal-Wallis test to discuss. It turns out that JUMP does not have Friedman test built in, so Friedman test is out of the window for tomorrow, but it does have Spearman rank correlation test, okay? All right.